So if the discriminant fxx fyy minus fxy squared is negative, then we at least have a plausibility argument that we have a saddle point, because if fxx and fyy have different signs, that guarantees that the discriminant is negative. Now, there are other cases where the discriminant is negative, and if the discriminant is negative, you are going to get a saddle point, but we're not in a position to really prove that. That's actually a proof that we need advanced calculus, more advanced calculus, to accomplish. So I'm going to say a few things that you're going to need to more or less take on faith. Now let's consider if fxx and fyy have the same sign. So if they have the same sign, then, as we've seen, fxx, fyy is positive. Then the discriminant fxx fyy minus fxy squared can be positive or negative, depending on how big fxy is compared to the fxx and fyy, and how big the square of this is compared to this product. If positive, then fxy isn't big enough to overcome the curvature dictated by fxx and fyy. In other words, the curvature in the x and y directions is, in combination, when you multiply the two together, big enough to overcome the opposite effect of the fxy. So if the discriminant is greater than 0, then either fxx or fyy dictates whether you have a max or a min. It'll be one or the other. Now you can read the specific breakdown of the rule in your textbook. Your textbook says that basically most textbooks will say, well, if d is greater than 0 and fxx is positive, that means you have a minimum point, because that means you're going to have positive curvature and your critical point will be at the bottom of that curve. It'll be a minimum. And if fxx is negative, then you're going to have a downward curvature and your critical point will be at a maximum. If fxx and fyy have the same sign, which is necessary for fxx, fyy to be positive, then both will either have a minimum at the point, the curvature will be in the same direction, whichever direction you move in, or they'll both have a maximum. They'll both have negative values, and you'll have the peak of something that might look kind of like a paraboloid in the neighborhood of your critical point. So we can make the statement, if xxx is greater than 0 then so is fyy, and either indicates a minimum. If fxx less than 0, so is fyy, and we get a maximum. I'm not going to write out the whole statement. It's completely analogous to this, and the reasoning is identical. And it might not be completely clear, but we're assuming that d is greater than 0. So for everything we say here, from here down, we're assuming that the discriminant is positive. So we can say that if d is less than 0, we have a saddle point. If d is greater than 0, then we have a max or a min. If d equals 0, which is the only case left, then it could be either. And we have to use something besides just this discriminant test to determine which. Point out that d can be less than 0 due to fxx and fyy opposite signs, or a large value of fxy. Okay, d greater than 0 means fxx and fxy have the same sign. fxy isn't too big. And this condition on fxy, in this case, gets a little bit subtle. I can't really explain to you without techniques of advanced calculus, at least not in any comprehensible way. I can't explain to you why that's the case. It relies on a Taylor expansion. Something you should be familiar with from first year calculus, but it's a Taylor expansion of a function in two variables, and it's a little more than we can really talk about right here. If d equals 0, then we could go either way, and we can give examples. Your text, I believe, does give examples of how d could be 0, and you could have a saddle point, or you could have a max or a min. For example, if it's an x to the 4th plus y to the 4th function, then all your partials are going to be 0. All your second partials are going to be 0, but you can still have a max or a min. So I'll just write down an example of where d is 0. If f of xy equals x to the 4th plus y to the 4th, then fx equals 4x cubed, fxx equals 12x squared, fyy equals 12x squared, 12y squared, and fxy is 0. The y derivative of fx is 0, y being the variable x being constant in that case, and the y derivative of fy, which I might as well write down, fy is 4y cubed, and I think I said it wrong, the x derivative of fxy, y being considered constant for x derivative, is going to also be 0. At the point 0, 0, we have fxx equals fyy equals fxy equals 0. So the discriminant is 0 without writing out the details. But the point 0, 0 is a critical point with a minimum of f of x, y at 0, 0. Very clearly this is a minimum, x to the fourth, y to the fourth. If x and y aren't both 0, these are going to both be positive, and at 0, 0 you get 0, so it's very clear that this function does have a minimum even though its discriminant is 0. And we could give an example of a function with a saddle point. We'd have x, y terms, but we're not going to do that now. As an example, let's consider the function f of x, y equals x cubed minus x squared y plus y squared. The x derivative is what? 3x squared minus 2xy. The xx derivative is 6 minus 2y. Y derivative of our function is negative x squared plus 2y, and fyy then is just 2. fxy would be the y derivative of fx, or the x derivative of fy. So we could calculate this as 3x squared minus 2xy derivative with respect to y. That's your fx derivative taken with respect to y, and that equals negative 2x. X being treated as a constant throughout. Fyx is the x derivative of xy. Well, the x derivative of fy. I think I said that wrong. Fy is negative x squared plus 2y, the x derivative being then negative 2x. Y being treated as a constant, it should be clear that we get this derivative. Now where does this leave us? Well, we have all our derivatives. Our critical points are going to occur when fx is 0 and fy is 0. So if we want to find our critical points, we set fx equals 0 and fy equals 0. Fx is 3x squared minus 2xy, so that should equal 0, and the fy is negative x squared plus 2y, which should at the same time equal 0. We get then this set of simultaneous equations. And I've just realized that this has been concatenated on the back of another video, so I'm going to stop this here and we'll continue in a minute. The video is long enough as it is.